And this method is very powerful and very easy to use. Even you don't need to do any experiments. Just based upon your childhood playing the bubble things, that will help you. Okay. So basically here the membrane analogy is this: all the torsion, the shaft under torsion, for study the distribution of the stress, and that can be make analogy to study the shape of membrane that is pushing bulge by pressure. You simply study the shape of the membrane that can be mimicked exactly to mimic the distribution of the strain stress, and that's it. So the remaining is I will show you what is the principle here. So in terms of the concept, you imagine there's a circular ring, and there's a bubble film, and then you blow it from the bottom here. So this is top view, this is side view. You blow it, the pressure, you try to pressurize from the interior. So that would be the shape the membrane, the film will be. Okay. And study the gradient study the gradient of the film diffraction. The gradient of the film diffraction can tell you in a mimic on the same shape of the cross section. Study the gradient of the film diffraction. That will tell you the distribution of the strain stress. So that is the thing we're going to study here. On Blackboard, I have uploaded, I think, quite a few the manuscript or the files. Some of them is I written by myself, and some are I found it from online. So hopefully those reading can help you building up more foundations. But here I just kind of quickly, kind of conceptually address the more important key things. Okay, so that is the one, and how that works. And later, if I have time, I will give you the whole list of the one-to-one analogy between the membrane and between the shaft. For example, on this slide, it's kind of boring, but this column representing is the mathematical governing equations for describing the diffraction of the film. And zeta, the node is the vertical diffraction. The larger the pressure, the larger the zeta. And P is the pressure we apply, S is the surface tension. And this is the governing equation for describing the torsion of the shaft. The phi is we call the stress function. Once we solve for phi, then the strain stress, the angle of the twist, or the displacement vectors can be derived quickly. And that one, I think you have seen that before. This one? Okay, probably you saw this one. So this one, if we solve for this function, then everything will be derived automatically. We're concerned is about the stress, and we're concerned is about the torsion loading. So this is the one I mentioned here. Okay, so from here you can see we compare one-to-one. Basically, that is the same mathematical equations. So if we solve for one, basically the other one can be mapping and then exactly know. And so in this way you can see sometimes in terms of doing experiments, doing twisting and measuring the strain stress is more challenging than doing the experiments of measuring the diffraction by applying the thin film. So people using this one to kind of indirectly to quantify the behavior of the torsion. And from here you can see by comparison, at least we can say this function is limited to the diffraction. The whole thing P over S is reflected to 2G beta. Beta is the trace of angle per length. So from here, we'll be able to do something. And from here, this is the table of the analogy. And later, I think I will utilize this table to show you quickly to make a conclusion of this chapter, but we'll leave this behind. So in mathematics, this one, we can really do the things. If you want to go to quantitative calculations, utilize this table. And again, I will use this table to show you one example. But before we do that, kind of the boring things, then let me show you some qualitative analysis. Again, this one I summarized is the one-to-one analogy of the things. So basically, here is the cross-sectional shape of the membrane, which means that is a supporting ring, and also this can be the cross-sectional shape of the shaft. And this dashed line representing on one side representing is a contour lines of the deflection of the membrane. You could imagine the membrane is protruded out of the board and pressure is on the other side. Or these contour lines can be the contour lines of the phi, that's spatial function. And again, remember the spatial function is related, can be used to derive stress. Okay. At this moment, I think I need to write down some principles, and then we can follow up, we can proceed to analyze the things. And again, using membrane analogy method, in particular, we want to know the distribution of the stress. So here is the membrane. Here is the shaft. For example, we concerned is about the shin stress. And shin stress is proportional to the gradient of this spatial function. And the spatial function in membrane is an analog to the diffraction. Okay, so that means you can see the shin stress in analogy. We're simply looking for the gradient of the contour lines in the membrane. Okay, so keep this in mind. Before I move on to the next stage, and let me ask you one question. If we're looking for a place where the larger shin stress occurs, so which region on the graph we should looking for? If we're looking for, if we try to look for the larger shin stress, then basically what we're looking for is where the gradient is large. The gradient of this one is large. Okay, keep this in mind. So keep that principle in mind. Then here we begin. I try to graphically to demonstrate how to utilize how to visualize the gradient of the contours to determine the shin stress. For example, if we consider here is the square shaft, and that is the things here. So this is a cross section. We make the cross section to analog to a membrane is under pressure. So a membrane under pressure, there will be force like this, and so the contour lines. So here, for example, here is showing here is from the fourth side. If we take the diagonal sides, that will be the elevation of the membrane. Okay, and from the 3D view, that is a contour lines here. And from the middle line, that it should be like this. And now the question is this. So where, in terms of the membrane, so where on this domain, that gives us the minimal, the gradient of the contour.
The minimal?
The minimum or smaller. Where? Let me say corner, middle, top. Top could be the one, and also corner. So those is where the large string stress could occur. Again, the string stress is related to this one. So that means for in terms of the square, you can see the square shaft under torsion, the corner will have much less string stress. So likely you can cut it or you can round off the corner to save certain material. And the people saying the stress concentrations would occur really at the corner, but not for this case. No. If saying, hey, you get a square, then square corner, then here the 90-degree corner, then the stress concentration would occur. You say no. By theory, it shouldn't be. That is where the less stress. Okay, from here you can quickly tell. And the next page.